like Keith is just joining. Maybe we can wait just a couple of minutes.
Okay.
Sure.
And see if more people maybe, maybe Riley and Doug and, some other people.
Sure.
Yeah, I apologize what I sent you there. Stan said, Dan, you need to toot your horn a little bit. I'm like, yeah, but I'm not really into that, Stan. He says, Dan, you really need to. I've seen your resume. I'm like, okay, I'll have to pare this down somehow,
So you and Stan both. I mean, my God, his resume is like, you need a dot matrix printer to print all that.
It's called staying busy.
Yeah, staying very busy.
Yeah.
Now, Stan and I are both military brats, so you got to understand we've got histories. I mean, we both have records that go back into our teenage years. We can't escape from. So
yeah, you and me both.
So Peter, I think what Dan's going to do is, if you allow him to share screen, he'll probably run it from his computer.
You should be co-host, and you should be able to share screen on your own now.
Yeah. Okay. Well, we'll do it that way. And let me pull it up here.
So I tell you what, while we're waiting for a few more folks to drop in, I'll kind of start introducing Dan. When I was doing my show on Think Tech a couple of years ago, I somehow came into contact with some emails and analysis that Dan Gowin had cranked out and ended up in my in basket. And I read them and I went, holy mackerel, this guy has a pretty broad, grasp of worldwide energy, just everything, oil, natural gas, coal, techniques for drilling, techniques for mining, techniques for, even nuclear power. It's like, how does somebody know all this stuff? And then I get to know him a little bit more and try and get him on my show, and he's too busy. So it took me like a year to finally get him on my show. But in the process of talking to him and trying to learn about, what gave him such a broad background, we became pretty good friends, and we shared a lot of information together. And like you said, we have common backgrounds as kids growing up with our parents in the military, and which is a strange upbringing, period. I mean, I can't describe what kind of impact it has on you, but when your father's a Marine, you're a Marine. And you didn't sign up for it. But it's an interesting upbringing. So anyway, Dan has actually got an incredibly varied background. And I'll let him talk more about that to what degree he wants to, but he professionally now does a lot of information work on computer programming, network programming for life insurance companies, for power grids, for you name it. He does a lot of computer work, but he's also got a lot of heavy technical background on industrial stuff. And then he was in the Navy before, did some pretty interesting stuff that we really can't talk about. But even after he got out of the Navy, he did a lot of defense work as well, on weapons and things like that. So he's got a really interesting background. But today he's going to talk to us about geothermal, partially because I knew that, we've been talking at Sustainable Energy Hawaii about geothermal for the state. I've been talking with the folks that I work with on hydrogen about geothermal for the state. And when you get right down to it, the scale of fossil fuels right now is pretty much incomprehensible to the average human being. The amount that we depend on fossil fuels, and to make a transition from fossil fuels to some other kind of energy production is a huge leap. It's not a jump, and we're not even handling it like a transition. We're trying to leap over the Pacific Ocean from California to Japan in one bound, and it's just like you just can't do it. So we've got to go through a transition, and part of our discussions, Dan talked about some projects that he and his family have worked on, and he'll go over those today, dealing with geothermal. And he's going to propose some things, and Peter's seen some of this before, about how we could actually start converting things like nuclear power plants and coal-fired power plants in place, and keep most of the infrastructure, including all of the easements and wires and substations and generation and all the stuff as it is, and just change the source of the heat to drive the turbines. And so we can get started at any time, Peter, as soon as you give us the go.
Oh,
All right, Dan, all yours, buddy.
All right. So my name is Dan Gowin. So my background, I would like Stan and I were talking about, I'm a Navy brat, so I grew up in Japan. Most of my family is nuclear Navy. So I've got a couple submarine captains in my family. My dad, Michael Jim, were senior chief petty officers. My dad retired out of the Navy, ended up working for the Department of Energy. My daughter, she's in the Navy. She's nuclear Navy. She's nuclear Navy. So, and as far as my military career, Army, Air Defense, South Korea for a lot of years, came back to the States. My dad retired. When he retired from the Navy and went to work for the Department of Energy, he went to work out of a place called the INL, the Idaho National Engineering Lab. That is a research and development center for nuclear power. Okay, so that's how I know a lot of things about the utility businesses, because I was a 14-year-old kid growing up in that lab. Well, when I was 14 years old, this research scientist, back in 1979, so I'm dating myself, gave me this 9-track reel-to-reel tape, and I loaded on a DEC PDP-7 mini computer, and that computer ended up being machine number 11 in the National Science Foundation. So I've been working on the ARPANET project since I was probably about 14. So you'll find a lot of the internet standards have my name on them. So I mainly wrote NTP on a number of patents on GPS. I own 4 patents on GPS. Out of the 31 Navistar GPS satellites, I own 4 of those patents. When I left the military, I ended up at the Crane Naval Surface Warfare Center in southern Indiana. And started out with JDAM, and of course there's a ton of classified projects I got to work on. Stan and I talk back and forth about some of that. When I left the Department of Navy, I was a GS-15 Step 3, so I was about as high as you could go. When I left the Department of Navy and went to work for Indianapolis Power and Light, that's an AAS company. It's a public utility up here in Indianapolis. And I automated everything that was bolted down, put in the fiber optic backbone, the city of Indianapolis, cell phone towers, and I can go into the complete control system that I designed for IPL for the city of Indianapolis. From there, I went to work for a place called Mid-Continent ISO. And what I did is I took that same system, it's called WMIS, Work Management Information System, and I stretched it over 26 states. So I'm the guy that designed the computer system that controls the power grid in the United States for 26 states and parts of Canada. Did some time automating everything at Eli Lilly, so I've got a lot of that type of background, everything from industrial processors for manufacturing drugs, vaccines, things like that. And then after spending about in between there, I did a number of projects for General Electric, and that was their alternative fuels program down in Evandale, down in Cincinnati, and that was burning hydrogen in gas turbines. So a lot of people come to me, they're always surprised, like, Dan, you've got a really great background in gas turbines. You seem to know a lot about steam too. Well, if you're in the gas turbine business, you know something about what's called combined cycle. And combined cycle is basically where we take the exhaust from a gas turbine, use it to heat up a boiler, produce steam, and use that to drive steam turbines. And you can take your 50 megawatt gas turbine and turn it into like a 200 megawatt power plant, basically, or a 657 megawatt gas turbine and turn it into a 1.6 gigawatt power plant. So that gave me that kind of background. Since then, I've kind of wandered off in the corporate world, and I'm on the board of a couple different companies, sort of like Stan and Electrum Power and Technology. Primarily, what I do there and some of my other subsidiaries is I provide a lot of IT support. When I built the system there at Mid-Continent ISO, an independent systems operator, not only does that system control the power grid, but I also developed the energy markets there. So there's a spot market, futures market, and the long-term power systems. power control system, therefore financial systems. And because of that commodities futures type background, when I develop those systems, I usually get drug into doing work for banks, the Treasury, the Federal Reserve. That's what Stan's talking about. So I'm the guy. I've got real-time data coming in from gas and oil wells. I know how much gas is flowing through the natural gas system because that's just part of my business. I have to report up to these other people. I'm all besides what I do for either the Treasury, the Federal Reserve, or the banks, and I'm usually one of the people down in the guts of the system. I see the flows of capital and energy through the system. And that's what Stan's talking about, because I'll be talking to Stan. Well, so-and-so is going to happen, and about 3 or 4 weeks later, it shows up. It's like, Dan, you told me this 3 or 4 years ago. I said, yeah, because I can see it in the system. And it's just now that they're finally acknowledging something's occurring. So that's kind of what he's talking about. Any questions so far before I kick this thing off? Okay. Good. And share my screen out. Everybody can see that, right?
Yep.
Yeah. Yes.
So that's just my logo, and I got this nice little graphic in the background. It makes it a lot easier to kind of explain to people kind of what the company is about. If you're interested, I sent to Peter, the host, this PowerPoint, and he's free to distribute that out there. Of course, Dan has it also, and he'll hand it out. So we'll go to the next page. So what are we talking about? Geothermal power. Okay, what this is based on, and it's actually based on a program that the Department of Energy has, and it's called Enhanced Geothermal Systems. And what it's based on, and understand this is just general numbers. It's not a perfect measurement, but it's a pretty good ballpark to measure things by. And what it's based on is every 2,000 feet you drill down in the crust, the temperature increases by 30 degrees Fahrenheit. Of course, you can convert that to Celsius. And everybody's heard the tales of, for example, like the gold mines down in Africa are dug so deep, a couple miles down, and it's so hot down in there, the poor miners, you got to have air conditioning, and it'll burn your hand just to touch the rock. So that gives you a good idea what we're talking about. So today we're going to talk about depleted oil and gas wells, right? And then we're going to go to medium geothermal, and then we're going to go into some of the deep geothermal, and that goes in what Stan is talking about. We could probably take existing power plants and retrofit them using this type of technology. And believe it or not, we actually have the ability to drill down to that 40,000 foot level I'm just describing. I'll show you right now. What's even more surprising, ladies and gentlemen, is that we have been doing this for at least the last 30 years. So it's not new. That's probably going to be the more shocking. Go to the next slide. Okay, so geothermal power can be broken up into 3 different groups. So you've got a shallow geothermal, 5,000 to 10,000 feet. And believe it or not, between 5,000 and 8,000 feet, that's most of your depleted oil and gas wells are that deep. Medium geothermal, 10,000, 20,000 feet. Believe it or not, the guys who are out there horizontal drilling and fracking shell, those are the levels they're drilling for shell. Believe it or not, the shell is actually below where you normally find oil deposits. Usually oil deposits are between 5,000 to 7,000 feet deep. And the shale rock, it's a source rock, it's actually underneath that. So these shell drillers are already drilling down to this 10,000 to 20,000 feet level. Not only that, but they're doing the horizontal directional drilling, hydraulic fraction rock, that kind of thing. And you can see some of the temperatures you can down at those levels. It's 150 to 300 degrees. And then you can go down to deep geothermal, which is 20,000 to 40,000 feet, and you can get to the temperatures between 300 to 600 degrees. And that brings it into the range of some of the existing power plants, like, for example, that big GE steam turbine that's sitting behind me. You can see it's a 340 megawatt steam turbine. It actually brings into possibility being able to tap into geothermal hot water to actually drive one of these industrial sized steam turbines.
And just for a point of reference, down water boils at 212 Fahrenheit, right?
Right, 212 Fahrenheit. Yep. So we go to that. Okay, so shallow geothermal, 8,000 to 5,000, 8,000 feet. Remember I said this is most of these depleted oil and gas wells we have all over the United States are already at this step. What most don't realize is whenever they drill into an oil field well, what's actually coming on the ground is not just oil. It's actually a mixture of water, oil, and gas. The water is actually salt water. And what they do is they bring it up, they put it into a separator, and they separate the oil and the gas from the water, from this brine water. And they take the brine water and they pump it over and inject it into another well back down in the ground. And the reason why is because you don't want the salt water contaminating your groundwater. What most people don't realize is whenever this water comes up out of the ground, it's coming up hot, coming out of the ground hot. So that brings into possibilities some really, really interesting possibilities for communities if they really think about it. And we go to the next slide here, and that's exactly what's going on. The Department of Energy has a number of projects going on all over the United States where they're doing exactly that. Rather than plugging up these old oil and gas wells, what they're using it to heat communities. Most houses these days have what's called a heat pump. That's where you have central air and then an air conditioning box outside. Okay, that's called a heat pump. Well, what you can do is you can take your existing central air furnace and retrofit it for hot water and use that to heat your house. Since the water averages about 110 degrees Fahrenheit, that's hot enough to just basically pump that water through all these houses and provide heating for your house. The other thing you can do is that there's a form of geothermal cooling. And what that is you dig down 6 to 10 feet, you put pipe in the ground like a zigzag, and you can pump water through that and use that to cool your house. So the only thing you're really paying for in your house is pretty much electricity for the fans and the pumps to basically move hot water around. Either you're moving hot water around for heating, or you're moving hot water, or you're moving cold water around for cooling. So it's a great opportunity. Now, as far as the communities that are using this type of technology, Boise, Idaho, if you go look down at the houses on First Street all the way down to the Capitol building, they use this type of geothermal heating for all the houses. And it's the same, pretty old story. They drill the water well down into a fault. What's coming out of that fault is actually hot water. And they've been using that to heat houses in downtown Boise for over 100 years. The other place where they've done that is Seattle, Washington, downtown Seattle, all of the older houses downtown. Same story, drill the water well, drilled into a fault, hot water is coming up, and they're using it to heat houses. So it's not new, it's stuff that already exists, we're already using it. And all we're pointing out here is instead of getting lucky, drilling down 1,000 feet and accidentally drilling into a fault, right? We can use some of the drilling technology, actually drill deeper to actually construct geothermal systems. So we don't have to worry about drilling into an existing fault system, right, to get at the hot water. We can actually design systems where we can intentionally. Okay. So this is the medium, and this is where you go 10 to 20,000 feet. We talked about the shell drilling. What happened with the shell drilling, the shell revolution, is sort of a happy accident, is how I describe it. And that is what happened is they were drilling these wells too close together. And when they were horizontally or fracturing one well, what happened was that water contaminated the well next to them, and what was coming out of the ground was hot water. So it's kind of a happy accident that what's coming out of the ground was water at 300 degrees Fahrenheit. Now, you probably would not want to implement any of this in an existing area that has geological issues. So it's kind of important. You go out there and get with the geologist, do some test wells, understand your geology. But if you've got a geologically stable place, it brings in the possibility you can purposely build a power plant. First by figuring out where to drill these wells, and then figuring out where you're going to locate your power plant. Or if you've got an existing power plant, you might be able to retrofit an existing power plant. We'll talk about that. And in fact, one of those power plants was built. So this is a power plant called the Ormet Binary Geothermal Power Plant. Back in the early 70s, a rancher was out. The rancher was having a water well drilled out on his ranch land for his cattle, and he struck hot water. Back in the 70s, we had a pretty serious energy crisis. And the Department of Energy petitioned for some money from Congress, and they put that money to good use and basically built a power plant that runs on hot water. So it's able to turn hot water into electricity. Now, the beauty about this plant, it doesn't require that water be up to the temperature of boiling water, right? And we'll talk about how this power plant works. My relationship with this power plant is my dad worked on this power plant when it was commissioned in 1980. From 1980 to 2002, it was ran by U.S. Geothermal, and I think it was in 2002, Ormet went back and basically rebuilt the plant. Basically, they retrofitted it, put in some new parts. Ormet's a company they built. Instead of having custom parts for your power plant, they basically mass produce a lot of the components that you see down there in the picture.
I think this is very similar to PGV's technology, if I'm not mistaken. And Mitch, am I right that Ormat is like the parent company over PGV, or at least the guys who constructed it?
Correct.
Okay.
Okay. If you're ever been in the United States Navy and you've been in a submarine or aircraft carrier and you see a bunch of hardware that looks familiar, just remember that this power plant came out of the mind of a bunch of Navy guys. Okay, so that'll give you a hint. So, the next screen. So, as for how does this power plant work? Well, what we see here is down in the middle here. Where's my little cursor? Down in the middle here, there's a generator right about there. And then there's a heat exchanger here and another heat exchanger here, these long tubes. And you can see this long pipe going off in the distance. It actually wires back here. Why is that direction? Why is that direction? But so what they do is they've got a production well and an injection well. The production well, you actually will see a little bit of steam out here. That's the production well. They got hot water comes in, comes up here, passes through the heat exchanger, then the water goes back into the pipe and actually goes over here on this side as the water is injected back down into the ground, back down into the thermal reservoir. More than about 5,000 feet down underneath this site, there is literally a thermal reservoir of water, a lake of water. According to the geological reports I've read, it's something like 10 square miles in size. So they basically drilled down and fractured a lot of the rock underneath this site and pumped a lot of water down there to create this huge lake of thermally hot water. The temperature averages between 280 and 320 degrees Fahrenheit. The water comes back up. The real working genius of this power plant actually goes on inside this heat exchanger. Inside this heat exchanger, there's a fluid in there called isopentane. It's an organic fluid. Isopentane actually boils about 97 degrees Fahrenheit, right? And what it does is it boils, generates vapor. It's a fluid that has a low boiling temperature, lower than 212, right? And they use the vapor off the pentane to drive turbines for generating electricity. Right now, the power plant produces between 15 to 20 megawatts. When my dad worked on the plant, it was originally designed for 140 megawatts. If you've ever seen some of Ormet's other power plants, and you look at this power plant, Ormet's other power plants, if you notice that the heat exchangers are proportional to the generator, but if you look at this power plant, you'll say, well, first of all, those heat exchangers are different. Number two, they're a lot larger. Well, that's because originally the plant was designed to generate 140 megawatts worth of power. Why this plant right now is generating, down in that 20 megawatt range, my guess is it has to do with because they're satisfying the needs of what the customers in southern Idaho need on their power grid. Maybe sometime in the future, maybe they'll need that 100 megawatts. Questions so far? Okay. So we get into the deep geothermal. Deep geothermal, that's 20,000 to 40,000 feet deep, and the temperature is between 300 to 600 degrees Fahrenheit. Now, why would you want to consider this? Well, because this brings into probability a huge opportunity, especially if you're already in the utility business and you have an existing power plant. So what am I talking about? Well, talking about is this. This is basically retrofitting an existing coal-fired power plant. Since I have the ability to drill down to 40,000 feet and get access to water that's at 600 degrees Fahrenheit. That brings into the possibility of retrofitting an existing coal-fired power plant and turning it into a geothermal power plant. You'd also got another great. So this one here is a nuclear power, so pressurized water reactor here. The important parts here, you got your reactor pressurized 600 degrees Fahrenheit, and you got a heat exchanger in a reactor. It's called a steam generator. Now, I'm going to go back and forth between this picture and my next graphic. Here's the next graphic. Here's where you would turn that power plant into a geothermal power plant. Now, what brings us in a possibility is simply this, and that is going back and talking to the guys at the Department of Energy. The average size of the pipe coming out of a pressurized water reactor, the diameter is 18 inches. Okay, out in the Gulf of Mexico, the drillers and the big oil rigs that are out in the Gulf of Mexico, they routinely drill with 24-inch pipe, right? And they're already drilling down to these deep depths, that 30,000, 35,000 foot level already. So that means, and understand that when you're talking about especially power plants this size, whether it's coal-fired or nuclear-fired, these size power plants are always located next to rivers, lakes, or the ocean. And the reason has to do with cooling water. So a vast majority of these plants are already located right next to either a large river like the Ohio River or the Great Lakes or an ocean. So that means this very large, heavy drilling equipment where they use this 24-inch diameter pipe for drilling for oil wells is well within range of conversion over this type of power plant. I know, talking with Stan, I know that the power plants there in Hawaii are located within a couple hundred yards of the ocean. So that means there's a possibility that existing plants could be converted over to using geothermal. The other thing I know Stan and I talked about had to do with financing. Whenever you're building power, especially either coal-fired or nuclear-fired, a coal-fired power plant, those are usually between $500 million to $1 billion a piece. A nuclear-fired power plant, those are usually between $2 to $6 billion a piece. When you're dealing, especially if you've got a power plant that's being decommissioned, you've got to decommission the fuel and all the other components of it. The hard part about doing decommissioning, now you shut down your power plant, you've got this dead asset, you're not realizing revenue. It's something that everybody in the utility business really needs to focus on and think about. They really need to consider converting that plant to a geothermal power plant. That way, while you're going through the fuel decommissioning process, you can keep your power plant running. It's still servicing the community. It's still producing power, realizing revenue, and that revenue will help you get through the fuel decommissioning process. And the same thing, especially with some of the coal-fired power plants, there's always some kind of environmental cleanup or whatever from a coal-fired power plant. By converting that plant, the existing plant, to geothermal, that'll help you go through a lot of those decommissioning and or cleanup processes. And so instead of having a plant that you've had to shut down for various different environmental reasons, you're able to turn it into a plant that's actually better. Now, why do I say it's better? Well, in the case of a coal-fired power plant, you're not paying, whether it's oil or coal, you're not paying for fuel. In the case of a nuclear-fired power plant, you're not having to pay for nuclear fuel every 18 months. So this is actually a better power plant. This is the type of power plant where pretty much you really shouldn't have to shut her down probably once every 5 or 10 years, pretty much just to do maintenance on it and just replace parts. So it's a type of power plant that'll yield dividends probably for 100, maybe 500 years into the future. So it's a much better.
And just as a kind of a point of emphasis, this kind of transaction or conversion could happen pretty much anywhere on the face of the earth. I mean, we talk realistically, it's probably 70 to 80% of the earth. You could do this. You don't have to be over a hot spot of a volcano or anything else. So lapse rate going down at 30 degrees, every 1,000 or 2,000 feet is standard in the crust across the planet. And you're
every 2,000 feet, it goes up by 30 degrees Fahrenheit, every 2,000 feet.
So you're going into basaltic rock, which is pretty much the standard consistency of the crust down at that level, 6 or 7 miles down. So as an example, and we've talked a little bit about this. Of course, we haven't had any of the geology done on it, but the Kahi power plant over on Oahu it's across the street from the ocean. And you could probably even use offshore rigs to drill pretty close to shore and run the hot water across the street under the roads to the existing power plant and start converting out the gas turbines into turbines that run off geothermal power one at a time, and slowly transition Kahi power plant from the existing gas turbine fired to geothermal, and keep all the rest of the infrastructure there, the turbines, the generators, the power line, the high voltage power lines, transformers, and all that, and it connects right to the same system. So you're not getting new permits or new easements for any of the wiring or any of the routing of any of the electricity that's going out. So I think that Hawaiian Electric, if they can get the geothermal wells, test wells done, they could determine whether they could go into this and just change right over in place to geothermal. They don't have to be like in Puna or any particular location. So they could do that there. They might even be able to do it in Pearl Harbor at their other power plant, their other main power plant in Pearl Harbor.
Yeah, the other thing Stan and I talked about had to do with financing. When you're talking about these big rigs, or I think Stan, I sent you some articles about the contracting these big rigs. You could work in between $40 to $100 million a year. But it would take them less than a year to do a project like this, because they're not really drilling a lot of wells, especially when you consider how many wells, when these guys are looking for oil, how many wells these guys drill. So even if it was $100 million, you're talking about $100 million you'd amortize over 100 years. And the other thing about it too is you're not paying for fuel. So how much fuel are you not buying? It'll pay for itself. It'll pay dividends because you've got out of the whole cycle. I'm no longer addicted to LNG or to oil or to whatever fuel I'm using in that power plant. I've broken that addiction. The other thing Stan and I are talking about, because I have them, some of the systems I'm in, because I monitor what natural gas wells and oil wells here in the state of Indiana. We have some wells here in Indiana that have been here since 1890. They're pretty much maintenance free. The only thing you got to worry about is like what rusting of a wellhead or something like that. But all that means is I call a crew out there, hey, re-drill this thing. And if they have to put in a stainless steel wellhead, they put in a stainless steel wellhead. So, and as far as the rigs work in the saltwater, guys, they've been doing this work out in the Gulf of Mexico for, 80, 90 years. These guys are experts doing this type of work.
And just to put the finance piece into perspective too, when you're an oil person and you're out there trying to find oil, what's the percentage of hits on your drilling, Dan? Because I know it's a lot higher than.
To answer that, they hit oil or gas. It's like 1 out of every 20.
Right, and this one.
Most people be surprised how low it is. 5% of the time they hit pay dirt, meaning 95% of the time it's a dry well.
Yeah.
And you're spending a lot of money in dry wells, and that's just the oil and gas. And it's getting worse, by the way. It's getting harder and harder to find oil and gas. I watched a lot of the people out there that are talking about, we need to get into Wyoming and dig up this Powder River coal, or we need to be over here in Ohio or Pennsylvania, and we need to be drilling for all this shale gas. And people ask me questions about that, and I just scratch my head. I'm like, all those fields are going dry, guys. I can show you the data. It's a resource depletion problem. I know Stan and I have talked about this extensively in our videos, but for whatever reason, we can't seem to get through the narrative that's out there. There's a resource, but the point being is, when it comes to the drilling, guys, it's just an opportunity.
Peter's on board with that too.
One of the things that it's like what I've heard here is that one of the roadblocks to doing geothermal exploration is the front end cost is just too high. And I go, well, isn't this the same technology and the same process that the fossil fuel industry has been going through since day one?
Yeah.
And the thing is that there is no place on this planet that you can't drill and get heat.
Right.
It's just like there there is heat everywhere.
Well, and on
And
top of that, let me show you this. Let me click the next slide here. This is from, it's called Petro-Online. And understand, I deal with these drillers all the time. And this whole heat issue is actually a serious problem for the guys that drill these wells. Let me give you an example. Down in South America, there's this oil field down off the coast of, I think it's Rio de Janeiro, down in Argentina. I think it's off the coast of Rio de Janeiro. Okay, it's called the Campos. Okay, the oil is so hot, and I can tell you how hot it is. I checked it today. It's 875 degrees Fahrenheit, the oil. So they literally have this giant radiator cooler on the bottom of the ocean. They bring the oil up, run it through this radiator to cool it off before they can bring it up the surface to the rig. Because if they don't, it'll hit the air, catch fire, and burn the rig down. Yeah. So these guys are dealing with this issue. And if you can look at here, right here, it tells you right there, 5,000 to 20,000 feet. The shale rock, they're horizontally drilling and fracking, that's at 20,000 feet. And I know for a fact, because I talked to the guys over in Ohio, the water that comes out of those shale wells, it's at 300 degrees Fahrenheit. And as far as the big rigs, when they're drilling, and I got down here, was at the Deepwater Horizon, that big accident they had out in the Gulf of Mexico back in 2010, that was drilled down to 35,000 feet, guys. Right, and the deepest one was drilled in Russia, and it's at 40,000 feet in 7.7 miles, and that was actually drilled back in like '87. So they're already drilling to those depths, and this temperature thing I'm talking about. I mean, down in the Campos Basin, oil 875 degrees Fahrenheit. That's hot. That's hot oil. And what we're talking about is not looking for oil and gas. It's simply drilling two wells, fraction the rock between the two wells, pump water into one, heat it up, and then pull the water out of the second well and using it to generate electric power. As far as environmental impact, sit down and talk to your local mayor or the guy that's running your local town or whatever, and ask him if he has a wastewater treatment plant. If he's got more than 50,000 people, he has a wastewater treatment plant. So all the issues dealing with a wastewater treatment plant are exactly the same issues you would have to deal with this plant as far as environmental impact. So it's an incredible energy source. These guys are already using 24-inch pipe. If you pressurize the water, so it's super critical in the wells, and you're talking, the big gas turbine I've got behind me, its maximum pressure is about 140 bar, which is about 2,000 psi. For steam, that's pretty low, guys. That's nothing for steam. But the steam turbines don't require pressures that high. Like I've said, about 140 bar, which is under 2,000 psi. So anywhere between 700 psi to 2,000 psi. And like I said, for steam, that's really nothing. Most of your nuclear-fired power plants, the temperatures don't get above 530 degrees Fahrenheit. Reactors don't run that hot.
So I hate to ask you to do public math, but that gas turbine behind you is a 140 megawatt gas turbine, which can go.
No. This is a 340 megawatt steam turbine.
340 watt.
340 megawatts. Yeah.
Megawatt. So if you were going to put 340 megawatts of solar panels out in a field, about how many acres would that take?
I don't know. I mean,
five acres per megawatt.
Yeah,
5 acres per megawatt. Yeah.
So 1,500 acres of solar panels to do what that one turbine can do, and it's probably going to last a long time.
Yeah. This turbine behind me, all it requires is I would need to drill a minimum diameter would be at least 16 inches in diameter, minimum diameter, right? I don't know how many gallons per minute I would need, but as far as the water is concerned, I only need to heat the water up to greater than 400 degrees Fahrenheit, and that would yield me about 50 bar worth of pressure, and that's all I need to do to drive that machine behind me, that steam turbine.
Right.
So what does that mean? Well, that's probably between 25 to 30,000 feet down. So you don't even have to drill down to 40. 25 to 30,000 is probably more than enough. And obviously these drill rigs are drilling down those steps anyway. And I've got my last slide here. And this is a nice little piece of treasure from the Department of Energy. And in the middle here, you see this thing says EGS, that's Enhanced Geothermal Systems. So what we're talking about is this fracking technology where we drill 2 wells and we fracture the rock through the 2 wells. That's what this talk is talking about. And what the Department of Energy has determined is that the United States could be generating in excess of 10 terawatts of electric power using this type of system. We can replace almost all our power plants with this. And then some. That's a lot of power. So
Exactly. And so, like, to reiterate, if you're going to drill a well for oil and only 1 out of every 10 is going to hit oil, but you can afford drilling for oil at that return with one in 10 wells hitting, and this is virtually 100%. I mean, if you hit water instead of, before you were ready, you could call it a failure, but even then you could probably use it for one of the levels of geothermal power generation. Maybe not as big as you expected, but
well, even if you hit water too early, Stan, and depending what the temperature is, you might, you just take and drill right through the water and just encase it with concrete and then drive it even deeper. Because what you're really looking for is what is the temperature of the water. You're looking for how hot is the temperature of the water. That's really what you're looking for.
The bottom line is, if you can afford gasoline and oil at the rate we're drilling now, and we've drilled for the last 100 years, your risk in drilling dead wells is so much lower with this technology. You can afford to do it.
Yeah, this is something that now is going on. There's the Texas Geothermal Association, where it's a trade organization, and they're doing exactly that. They're developing old, retired well bores for geothermal. So they're really big into it, and it's moving along. But one thing that I wanted to mention was the people that we were just talking to from Arctic Green, and he's got, I think he was saying he's got 600 wells, across Europe and Asia and stuff like that. That their yield rate in drilling is 70%, not 5%.
Yeah,
70%. Yeah. Yeah, it's rare that you run into some kind of geological situation where you can't utilize it. It does happen. I think I told Tan when I talked to the guys Department of Energy, probably 80% of the United States is amenable to this technology. Maybe 20% is in what I call geological risk areas. But what you're saying is maybe in Europe it's 70%, maybe it's 30% is a geologically sensitive area. But even if you drilled 2 dry holes, well, that's actually what I'm looking for, is drilling 2 dry holes and using water to hydraulically fracture the rock between the 2 wells. The other aspect of this too is you don't have to use proponents and sand for the fracking. You just use water, and as long as you keep the wells pressurized, the pressure of the water holds the fractures in the rock open. Right. So, and the other reason why you want to pressurize it, of course, you got millions of tons of rock sitting on top of this water, this thermal reservoir that you got deep underground. Okay, and the pressure of the water itself is holding the fractures open. Because I mean, if you release the pressure, the weight of the rock is so great, it'll actually squeeze the water out. Then you have to go back and repressurize it. The beauty of that is, when you pressurize water like this, its thermal holding capacity actually increases. So if you pressurize it between your injection well, your production well, the hot water is coming out, and then those pipes are pressurized from the well all the way to the power plant and then back, it's completely pressurized. Its thermal capacity of that water actually increases. Right now, there's kind of a debate going on between myself and some of the guys, the gas turbine side. So gas turbines run in what's called Brayton cycle, which is gas, right? Steam turbines are Rankine cycle, okay? And there's some differences in the cycle. And what the conversation we're having is the Brayton cycle guys, they want to use supercritical carbon dioxide, okay? And basically pressurized carbon dioxide greater 1,025 psi to turn it into a fluid. and run it through these systems or try to do it. And more I look at this, I'm looking at it saying, you know, I would rather use actually just water to do, right, and use an existing system and use water um, running through my heat exchanger. Now, as far as between the heat exchanger and the actual steam turbine, I may still want to use isopentane, because isopentane is actually a better fluid for using for driving a steam turbine than water is, for a couple reasons. One has to do with the fact that when you take water and you bring it to a boil, it'll expand by 1,000 times. Okay, isopentane, of course, water boils at 212. Isopentane boils at 97 degrees Fahrenheit, and it expands by 1,600 times. So it's actually a better fluid for the steam turbine. The other difference is I'm not dealing with water. I'm dealing with an organic fluid, actually a hydrocarbon, which is a lot kinder on my steam turbine. In other words, my steam turbine is going to last a lot longer. Isopentane is actually one of the fluids that they blend into gasoline. So it's an actual hydrocarbon. It's a lot kinder to my steam turbine than what water is. If you've ever torn apart an old steam turbine, you'll notice all the rust. Okay. But if I ran isopentane through my steam turbine, I wouldn't have that issue. So
I think that's one of the concerns a lot of people have is they hear you're going to be running this hydrocarbon, potentially hazardous material, and what if it mixes with the water and we're pushing the water in the ground, and now we got groundwater contamination. I mean, especially right now in this state, groundwater contamination is a serious issue with the Navy. But this is a totally separate heat exchanger that transfers the heat into that liquid, into that other material. It's not commingling water with the isopentane. It's two separate systems.
Well, the other reason why they use isopentane has to do with, you're talking about a fluid that has a low what they call a vapor pressure level. In other words, if you expose it to the air, it actually boils away into the air. Okay, so let me put it this way: if you've ever filled your car up with gasoline and you've had that smell of that gasoline smell, that's isopentane. So we're talking about a fluid that if you expose it there, it'll evaporate. You know, it's sort of like acetone. Are you worried about acetone contaminating your groundwater? No, because it evaporates right into the atmosphere. So even though you might have some environmental concerns, right, as far as you being exposed to it or any of those OSHA type issues, those are issues that are A, known, and B, it's according to the EPA, it's at the low risk area. So when you compare it to, for example, when we use water in a steam turbine stand, we add a lot of things to the water to make it work. Okay, and I'm talking about things like we add a hydrazine to the water in a steam turbine. Okay, and we use that as an oxygen scrubber, is what we do, and a bunch of other detergents and things, so bacteria and stuff like that doesn't grow into the steam turbine. So when you start balancing those things out, here's what I did to the boil of water in my steam turbine versus the isopentane, you're going to say I'd rather use the isopentane.
Okay. Well, the reason I bring it up is because if there's one thing that's going to kill any kind of project over here, it's we run into contamination issues or issues like that. So,
well, even if you had an issue with that, you could switch over to butane or even ammonia, right? So those are other working fluids that you could use in that steam turbine.
Yeah, we just need to be able to address the safety and the environmental issues up front, honestly, because the people in Hawaii have been BS'd by so many big companies that make big promises, and then when the problem hits, they go, "Oh well, yeah, we mentioned that in one of our briefings," and they buried it somewhere, and and people get really pissed, especially if you're going to put a whole lot of money into it. And I think this is actually going to be the way to go. But if we don't do it right, we might as well not do it at all.
Right.
And I think most of the folks here, especially in sustainable energy Hawaii, that's kind of like their mantra. If it's not truly sustainable and safe, and respecting the environment and stuff, just don't even bother. So I know there's probably some questions out there from other people. I've seen a couple in the chat. One mentioned that on your chart there, we can't read the small print, but it shows Alaska and Hawaii as gray, and there's all kind of cool colors on the rest of the continental U.S. What does the gray area mean?
I think they just didn't study Alaska and Hawaii.
Okay.
There's no color on it, so they didn't put it in there. I don't know. I can't answer the
Well,
Department of Energy, but the
those are foreign countries, aren't they?
no. Well, I mean, when we're talking about geologically sensitive areas, I one of my favorite places is the island of Guam. The only downside with Guam is, if you know anything about the island of Guam, it's essentially a big peanut. It's essentially two volcanoes that rose up out of the ocean, and is sitting on a subduction zone. That's what the Marianas Trench is, a subduction zone. And I don't know if you would want to put this kind of power plant on a subduction zone, but yeah, you've got the same kind of problem throughout the entire country of Japan, because the entire country of Japan sits on a subduction zone. Maybe the Sea of Japan side would be a good place for these geothermal power plants, but who knows? But as far as like the isopentane, or you could use white naphtha. If you remember those old Ronson lighter stand, remember those, the Zippos,
Yeah.
right? The lighter fluid, that's called white naphtha. You could use that in there too.
Okay.
So there's a bunch of these fluids, and the other thing is also understand, if whatever kind of turbine you have, all these things have lubricating oils and stuff like that. So the fluids I'm talking about have the same risk as any kind of lubricating oil you put in this thing. I'm going to stop sharing my screen here, and everybody can see my background there. That's big steam turbine. But any of those devices have lubricating oil in it, mineral oil, and so the fluids I'm talking about, as far as like risk of contamination or carcinogens or whatever, is really no greater than the lubricating oil that they're already using in these big devices. So it isn't anymore. It's not a strange chemical. It's not something that everybody hasn't already been exposed to or don't already know. And that's the reason why I bring it up when I say, what's isopentane? Well, it's one of the things they blend into gasoline.
Yeah.
But it's
I'm
about
not sure.
30% of gasoline's isopentane.
I'm not sure what Hawaiian Electric uses in its eco power plants on Oahu, but I'm sure it's not any worse. Not any better than what we're talking about.
Well, I'm just saying it's no different. It's not any worse than anything you're putting in your car, because you got lubricating in your car. You're using gasoline. Like I said, isopentane is in there. White naphtha they blend that into gasoline. So it's just one of the things they blend into gasoline, and it's not like tetraethyl lead or something like that. It's just pure iso. What they're looking for is a fluid that has a low boiling temperature, and there are a couple other alternatives. One would be like isobutane, isopropane, propane. And of course, Dan and I talked about ammonia. And if you said, Dan, which would you rather use out of all of them? I said, well, I kind of like white naphtha myself. That would be a better one. I kind of prefer it over ammonia, because I think ammonia is a lot harder to handle than white naphtha.
Okay. How about questions from anybody on the call? Crickets.
Oh, I was busy typing.
Oh,
So
okay.
what I think I just heard is these geothermal wells could very often fit inside the fence of a lot of these campuses where these existing, thermal, meaning, coal, diesel, or gas power plants are.
You could, but here's the thing. If you're gonna drill geothermal wells, don't use small diameter pipe. My recommendation is, off the bat, use 24-inch pipe. That's 2 feet in diameter pipe. The drill rigs for that sit on the rigs. The drill rigs sit on those big rigs they float out in the ocean, those type of rigs. So your limitation is going to be, how do I move around a giant rig? How do I move around 24-inch pipe? That's going to be your limitation. So that's why Stan and I were talking about, if we bring a drill rig, and these things are huge, they're multi-billion-dollar type devices, you bring it so close to shore, maybe you'd have to lay out basically a bunch of barges that go from your beach all the way out to that rig, so they can drag that equipment onshore, set it up, consume 12 months drilling all these wells, and then drag it back out to the rig. This is big, heavy stuff. This isn't stuff you're going to drag down your highway, guy. You can't put it on the back end of a semi truck. So
Not
your
a logging truck,
limitations,
like we got for Ohonua. We got a tree burning plant that's not open yet. You can put one of these pipes on a logging truck.
Maybe I don't think it's I think you could put the pipe on a logging truck.
It's
I
the
don't
rig.
think the link, right? It's the rig, the drill rig,
Yeah.
because you're
Right.
talking about a drill head that's 2 feet in diameter. And think about the rig that's around that. And of course, this thing's going to extend, I don't know how many yards into the air. Go out on YouTube and look at like the Deepwater Horizon or one of those big rigs they use out in the Gulf of Mexico. That's the type of drilling equipment we're talking about. The good news is that getting down to 35,000 feet, the Deepwater Horizon, it only took 6 months to drill down to 35,000 feet. So it won't be there for long. It's just you got to understand the year when you're drilling your wells that things are going to be inconvenient. But once they're built and they're there, they're there. That's the best part about this. Make a big sacrifice up front, pay huge dividends for a very long time.
And one thing we didn't talk
Dan,
about during the presentation was the actual footprint of that that geothermal plant was one Walmart parking lot. The actual footprint where the turbines and the heat exchangers were. So you could, that part of the plant itself, other than having to put a big drilling rig there to get it started and then take the drilling rig away when you're done. But when you're all done, the footprint is really small compared to like solar panels, or certainly not as obtrusive as a wind turbine.
Yeah, how I explain it to people is this is a power plant that'll fit inside of a Walmart parking lot. So, and even if you had to go all the way to those 700 megawatt size generators with those turbines, that will fit within at least one of those units, maybe two of them will fit within a Walmart parking lot. And you're talking, I could probably cram 1.4 gigawatts into a Walmart parking lot using this type of technology. The only thing you have to remember is you want to place your production wells at your hot well, probably needs to be close to the power plant. Your injection well is probably going to be at least a mile away, maybe more, because remember, between the two wells, you're going to fracture rock between the two wells, and you're going to have to spaced those wells apart. So they're going to have to be at least a mile away. So there's going to be somewhere in here, there's going to be this pipe stretching out for about a mile, maybe 2 miles, where the injection well site is going to be. But other than that, as far as, building freeways over the top of a pipe or burying this thing in the ground or, making it out of sight, out of mind, that's probably pretty easy.
Dan, are you saying then that because of the size of these drilling facilities, that this is actually only practical somewhere very close to salt water? You just can't move these things overland?
Well, I know that we can drag that type of equipment up the Mississippi River, up into the Ohio River in southern Indiana. All the big coal-fired power plants are actually right next to the Ohio River. So here in the States, I know we could actually place that heavy equipment onto barges and drag it up the river. The reason why I know that is because we have a bunch of mills and stuff up here. We manufacture a lot of those big parts here in Indiana. We put those on barges and send them down the Ohio, Mississippi, New Orleans, and out to the rigs. So what I'm trying to say is, as long as you've got water nearby, you can move this big, heavy equipment. If you're trying to move it on the freeways, I don't know how that's going to work. The point is most of those big power plants are located next to water anyway. They're next to the ocean, a big river, a big lake. I can show you all the big, huge nuclear-fired power plants are all right next to the Great Lakes. Or they're next to a river like the Savannah River, or they're right next to the ocean, like down in California, like Diablo Canyon is right there on the Pacific Ocean. So that's, as far as getting this inland, there might be a possibility of building a huge big rig, that you could use for drilling 24-inch. But I'm talking about you would probably have to assemble the rig piece by piece to build a rig that big. As far as hauling the pipe, yeah, you can probably load that onto semi trucks or two. I don't know how long these things are. I think that'd be something you'd have to work out, but you could probably put the pipe on semi trucks or two semi trucks, or I don't know how you would do the logistics of that. But even the rigs, that probably isn't a limitation. If you got it in mind that, okay, I'd probably, if I'm 400 miles inland, I might have to assemble a rig this big from pieces. Maybe these guys can build these drill rigs into smaller pieces and then put them together, So that might be possible, because really all you need is a crane or something like that to lift the parts and put them in place. So who knows with human ingenuity? Who knows?
I think Richard had a question.
Yeah, and the way I understand it, it's not the geothermal heat that we have, and the usable geothermal heat is not very deep here on Hawaii Island, like below 10,000. And we already have water. It doesn't, we're not chasing around for water. So the whole underneath of the island is saturated. So there's the heat, and it's shallow, and you drill down there, and the heat just rises out of there and spins a turbine. So what I'm wondering about is, we've been talking about needing money, like 25 million to do exploration. I didn't hear you mention any exploration in what you were describing.
Well, as far as exploration is concerned, it depends on whether you're retrofitting an existing plant or whether you're building a brand new plant. If you're building a brand new plant, I mean, one of the first things you're going to have to do is you're going to have to do test wells and test drilling and understand what your geology is, and get together with a geologist. As far as financing things, understand that I'm not from the oil and gas business. I'm from the utility business. So the utility business is a very different business from oil and gas. Oil and gas business, pretty much they're dependent on, especially investing, okay, because it's a boom and bust type business. The utility business, we're a long-term business. I know somebody asked me one time, like when we built Mid-Continent ISL, how we did it. I said, well, understand that we all came out of public utilities. For me, came out of IPL, so I went to, I knew Mr. Humke and Mr. Hodewell, the president and vice president of IPL, and I had them write up a letter of credit. And so we got the letters of credit from all these other public utilities in the area, and we took those letters of credit, and we went to the banker and we borrowed the money to build Midwest ISL. And that's how we built it. As far as exploration, what you're talking about, we're not looking for oil and gas. What we're trying to determine is geological feasibility. So my guess is it would be a combination of a grant from your state and also some money from the Department of Energy. And as far as who would actually carry out the studies, of course, the drillers would come in and do the test drills and so forth, and do core samples, those type of things. And more likely, you would probably turn it over to like the University of Hawaii and their geological department, and also the experts at the United States Geological Survey to analyze the different core samples. So once you've done that and done that study, determine the viability, then the next thing is, okay, we're going to go ahead and put in a power plant. As far as financing goes, when it comes to financing public utilities, that's really a combination of your state, your rate board, and your existing utility, and exactly how they want to put together a credit structure. Whenever they put together a credit structure, that's basically a letter of credit, and it's signed off on your state government and your local utility, and basically they're determining if they want to take on this credit risk, and the rest of it just finance it to the bank. So as far as the cost, I'm sorry.
Go ahead.
As far as the costs are concerned, you would have to get with one of the companies that's in this field is Baker Hughes. I know Stan and I need to put together an interview with the guys at Baker Hughes, because they're the drillers. They'd be the ones doing this kind of drilling, to get a sort of a quote or an idea of what they would think that they would need to actually go out and do the drilling. And the premier company that has a lot of experience doing this would be is Ormet. Another company that has, probably close to 100 years of experience just in power plants is General Electric. And we'd have to pull in General Electric to find out, what would be the cost of retrofitting an existing plant, or with Ormet using their tech. It all depends on how many megawatts you want to go with. Ormet seems like they're pretty good at 10 to 20 megawatt power plants, and of course General Electric, they're good from 20 megawatts all the way up to the big 700 megawatt generators, and of course gigawatt power plants. So that's the point is that's really out of my purview. I'm not into doing that contracting. I know all the people that would do that type of contracting, but there'd be a lot of exploration. We'd have to do a lot of investigation to sort of answer all these questions that you're talking about.
Yeah, I'd like to make one comment, and that is back in 2007, 2011, I was in New York City at an Association for the Study of Peak Oil conference. And, you know, we had this big room and a huge screen, and they were in New York City now. And I was sitting in the room and they were talking about Hawaii. And they said that Hawaii was the most oil dependent state in the nation. And also we had the highest electricity rate. So that was 2011. 10 years later, we're still the same place. We haven't done anything. Now, but the question I was just wondering, do you have a sense, like I've been going to these peak oil conferences and I'm feeling like, holy smokes, you know, the oil and gas is probably going to be declining at some point in the not too distant future. How do you see that? Do you hear that, or
okay, so Stan knows this. If you're asking me, you're asking a loaded question, and I'll tell you the truth. Okay, yeah. And that's the reason why Stan and I go back and forth. Before a month ago, I probably talked to my directors of the Department of Energy probably twice a week. These days, I'm in emergency calls with the Department of Energy every day. Okay. And it has to do with something that's been brewing over the last couple of years. So I'm gonna talk a little bit about the politics. Okay. I'm not gonna delve into the politics, as I know people have different opinions back and forth. Okay. But there's this truth that's sort of in the middle, and then there's these two political camps in DC. And I stand, the director of the Department of Energy, the Department of Defense, we're all ripping our hair out. Look at Stan and I, we don't have any left. Okay. So what it is simply this. And I can explain what's happened by talking about coal-fired power plants. So in the utility business, I have enemies on both sides. Okay, let me talk about my enemies. So the environmentalists, they don't like me, and the coal and the fossil fuel guys, the oil and gas guys, they don't like me either. Both of them don't like me. And the reason why is because what happened to coal-fired power plants. I'm responsible for taking a number of coal-fired power plants, gutting them, ripping the boilers out, and putting in gas turbines. And the reason why I put in gas turbines wasn't because I switched it from coal to natural gas. It's because I had a big building there and I needed something that could generate 557 megawatts worth of power, and I could do it in, like 30 minutes, right? In case there was some kind of a big power plant outage and I needed to fire up something really quick to generate a lot of electric power to really replace a hole in the grid. And then there's this whole wind farm stuff. I can't say we've got some solar farms up here in Indiana, right? But we have a lot more wind. Okay. So what happened was simply this. What took out the coal-fired power plant was the coal. So coal, and this is true with all fossil fuels. Let me describe what happened to coal, and then you can extend that to oil, gas, uranium, a lot of these natural resources. Okay. So coal, not all coal is created equal. There are 3 different kinds of coal. There's this stuff called anthracite, there's bitumen, and there's lignite. Anthracite, 80% or higher carbon content. That's just this good coal we used to get out of Pennsylvania. Really wonderful fuel. Pure, no sulfur, easy to burn, didn't have to worry about ash. Right. That coal has been gone for 40 years. The only place you see that coal is sometimes the guys use it for making steel, and they pay a pretty penny for that stuff. It's expensive, really expensive. Thousands of dollars per ton. Bitumen. Bitumen is between 40 and 80% carbon content. Most of the power plants run that. Then we have this stuff called lignite. Lignite is 40% or less in carbon content. It's brown coal. In the business, we call it burning dirt. Over in Germany, they just fired up their coal-fired power plants on the Germany. What they're burning? They're burning lignite. Now, if you want to understand this, is that when you burn these coals that are high in ash content, you have to run the scrubber. You don't have a choice. Even if we went to Washington, D.C., fired the EPA, bulldozed the building, you still have to run the scrubber. And the reason why you have to run the scrubber is you have to run, for these high ash content coals, you have to run the scrubber for two reasons. One reason is if you burn that coal, your employees, they live within 60 miles of your power plant. Every morning they get up, they'll scrape a 1/4 inch of ash off their pickup truck. Eventually it's going to dawn on them, oh my God, what am I breathing? And that's your employees, okay? The second problem you got is you're raining ash 300 miles around that coal plant. And you're raining that ash down on a farmer's fields, right? And there's mercury and cadmium in that ash, okay? And what happens when that heavy metal hits that farmland, it contaminates the soil and the crop yields drop. Farmers have hundreds of millions of dollars worth of property, and they're responsible for growing millions of dollars worth of crops. And whenever their crop years are falling, they go out to U.S. Ag, do soil samples, say, why are my crop yields so crappy? And they'll say, well, that's because all this coal ash coming from that power plant. So if you turned off your scrubber within 14 minutes, you're going to be in a federal court being sued by a farmer for violating his civil rights. Because in the United States, according to the Bill of Rights, and if you own land, you have rights, civil rights. And this farmer is going to be suing you for damaging his land. And so not only will you pay for the drop in crop yields, okay, because he's got like crop insurance and the insurance companies are coming after you. You got to make up the difference to the insurance company. And then you got to pay to go back and remediate all that soil. You got to dig up the top 10 feet of soil, extract all the mercury and cadmium out of the dirt, right? And somewhere in that process, your public utility goes bankrupt. So you got to run the scrubber. To make matters worse, that scrubber consumes half the power coming out of your steam turbine. And I'm just talking about burning bitumen. When you get down into burning lignite, that brown coal, think about it, 40% carbon content. That means 60% of it is not carbon. It's not energy produced. You have to burn twice as much of that stuff to make it work in your power plant. It means you got twice as much ash. And down at the coal mine, when they're digging this stuff up, they use the front loader, it burns diesel. The dump truck burns diesel. The train, the locomotive train burns diesel. The high price of diesel fuel will put your coal-fired power plant out of business. So if you want to know why I took a bunch of these coal-fired power plants here in Indiana and Ohio out of business, that's why. It was because of the coal. At the same time all this was happening, the wind turbines got really cheap, got really cost effective. So if you look at it from a megawatt for megawatt basis, comparing a coal-fired power plant to a wind farm, the wind farm's cheaper. Not only that, but when it comes to financing, if I go talk to the banker, and let's say I want every 50 years you got to remodel, rebuild your coal-fired power plant. The first thing he's going to ask you, what do you burn? If you say lignite, he'll tell you no. But if you say, okay, I'm going to put in a wind farm, they'll say, okay, we'll do that. So those wind farms are actually cheaper to install on a megawatt for megawatt basis than it is that coal-fired power plant. And that has nothing to do with just environmentalism. I'm just talking, that's just the practical aspects of this business. The fossil fuel business has the exact same problem. If you watch the shows that Stan and I did, right, some of the earlier shows, and some of those shows I talk about, there's an oil refinery up in northern Indiana, up in Gary, called the Whiting Oil Refinery. And originally the oil refinery was built by Standard Oil back in 1890. And the oil field they were tapping into was the state of Michigan. The state of Michigan sits on a salt dome. The entire state sits on a salt dome. And oil and gas collects underneath that salt. And what's happened up there in Michigan, Michigan has 36,000 depleted oil and gas wells. So that oil field went dry. Whenever that went dry, the Whiting Refinery started pulling oil in from the Great Lakes from Canada. And then from Canada, over by Niagara Falls, there's a locks over there, which gets them out to the St. Louis Causeway, the Atlantic Ocean, That's Nigeria, the Gulf of Mexico, etc. And that's the late. So they're pulling in oil from the other side of the planet into this oil refinery. Not only that, but the oil they're pulling in, it's not the good stuff. 50, 60 years ago, we got this really good oil. It's called sweet, low in sulfur, easy to refine, easy to turn into diesel and gasoline. Most of the oil we have out there right now, if you go out to oilprice.com, up there in the upper left-hand corner, there's a little clicker thing, and it'll say all oil charts. Click on that thing. And what you're going to find out is that most of the world's oil, what we call sours. When they say it's sour, that means oil with sulfur in it. Oil with sulfur in it, what they do to take the sulfur out is they do something called steam reforming. They use hydrogen to remove the sulfur from the oil. Well, that process of producing hydrogen is from natural gas. They take natural gas, steam reforming it, turning it into hydrogen, use that hydrogen to remove the sulfur from the fuel. So a lot of the natural gas prices you're seeing that are going up, part of the reason why the prices are going up is because they're trying to refine heavy sour crude, because the good crude is gone, like the coal. The good coal's gone. That's the same problem that's happened with the crude oil, is that the good stuff is gone. They mined it, they drilled it, they did that stuff first. Now the stuff we have is this crappy stuff, and it's real expensive to refine. And and even though these guys sit there and talk about, oh, we just drill for more oil, that would solve the problem. No, it won't. No, it won't. Because when they're running heavy sour in those refineries, that means that refinery is consuming even more natural gas. In fact, most people don't know the stats on this, and that is half of the world's natural gas is actually consumed by oil refineries. The other stat is the number one producer of hydrogen in the world happens to be oil refineries. The same place, right? So, and the reason why I answer that is because that's sort of one of these little hidden secrets that the petroleum business, they never talk about. Well, why is most of the hydrogen generated from steam reform? Well, who's actually using all that hydrogen? They'll say, oh, it's industrial processes. Oh, part of it's like 30% of it's actually making fertilizer, 30%. 50% are the refineries, but they never talk about it. So that whole situation is becoming probably a bigger problem. The biggest Achilles heel we have is actually diesel, right? If you want to know the economy's Achilles heel, it's actually diesel. The world economy runs on diesel. The reason why the front loader burns diesel, the dump truck burns diesel, the Class 8 semi-truck runs diesel, right? The locomotive train runs diesel. Oh, and here's the big one. There's out there something called the IMO 2020. It's a fuel standard for those big cargo container ships. 3 years ago, those big ships used to run bunker oil. Today, it's illegal to run bunker oil. You know what they're using? They're using something called very low sulfur oil, VLSO. VLSO is 75% diesel. Guess what? Nobody bothered to go back and re-engineer the refineries that they would have to double the output of diesel coming out of the refineries, because nobody thought about it. So the big cargo container ships switched over to basically using diesel rather than put a scrubber in my ship, rather than switch over to liquefied natural gas. They said, no, we're just going to start using more diesel, right, in our big cargo ships. So they've increased the demand for diesel, but they didn't increase the refining capacity and all those things. Now, why is that an issue? Well, Stan, there was a shortage of diesel in China last year, right? You and I talked about it on the show.
Yeah.
Last year. And now we have a shortage of diesel here on the eastern coast of the United States. Understand, this was all brewing long before the war with Ukraine. The world produces about 100 million barrels of oil a day, and the world consumes 100 million barrels of oil a day. There's no extra capacity. And a lot of us have known we're coming up to this time where there isn't any extra capacity for quite a while. Let me give you an example of what I'm talking about. And this has to do with math. There are people out there in the oil business that basically lie through their teeth to your face. Let me give an example. Saudi Arabia. For 20 years, Saudi Arabia claimed they could produce 20 million barrels of oil per day. I'll stand right here, and I'll tell you right now, they're lying and have been lying for at least 15 years. How? How do I know that? Well, it's very simple. Every time these guys say we're producing 12 million barrels of oil a day, if you go back and look at, there's a company called Rystad. Rystad, they book all those big oil tankers, okay? And you go back and look at their numbers, and those numbers quickly tell you that Saudis aren't producing 12, they're only producing 11. How do I know? Because only 11 million barrels a day was loaded onto those oil tankers. That's how I know. The other thing I know, they can only do it for about 3 months, and then the production drops back to 8.5. And you say, well, how in the heck were they able to do 11 million barrels of oil a day for 3 months, right? Well, how do I, well, see, to figure out what happened, if you go into the Gulf and they have big storage tanks all around the Gulf of the Persian Gulf there. And if you go and count up all the rental or storage tankers, you'll add all those up and you say, that's where the oil came from. So whenever people weren't using much oil, the Saudis snuck and stored a bunch of oil in those tanks. And so for about 3 months, they're able to produce 11 million barrels a day. So today we're going to the Saudis saying, we need for you to be producing that 11 or 12 that you said. And the Saudis aren't able to do it. And everybody thinks, oh, they're just holding it back. But guys like me, because I watch the computers and the data, and I can track it going back 15 years, no, guys, they've never been able to produce. There's another way I know it too. Let me tell you what it is. And I kind of alluded to it when I talked about on the show here. When that stuff comes up out of that wellhead, whether it's water or oil, it comes out hot. So one of the things I can do is I can pull infrared data off of the wells that are in Saudi Arabia. I can tell which wells are producing oil and which ones aren't, because the ones that are producing oil, they're hot, okay? And when you start looking at the diameter of the pipe coming out of the ground and the wellhead, and by the way, I get data out of Schlumberger and what's the other? There's Schlumberger and there's another one, Halliburton. That's the other one, Halliburton, and they tell you what the size of the wellhead is, because they make those like in standard sizes. So you say, okay, here's the diameter of the pipe, here's the wellhead, here's the maximum flow rate, and you start adding that up out of Saudi Arabia, and you come up with 8.5 million barrels a day. It was impossible for them to produce 12 million barrels of oil a day, and that's just Saudi Arabia. The other thing I know about Saudi Arabia, and if you've ever gone out there and seen any of the documentaries out there on this subject, right, you'll find out the Saudis have been pumping seawater into that Gowin oil field for the last 20 years. Here in Indiana, the only time we start pumping water into an oil well is because we're on the downward slope of production and she's going dry. And we use that water to increase the oil we're getting out of the well. So the sheer fact that the Saudis have been pumping water into their oil fields for the last 20 years tell me that they're going dry. It's just like, let me give you another one. Stan and I did this in a show. We talked about Alaska. Remember we talked about Alaska and that natural gas pipeline up there? Remember what I showed you? Here in Indiana, you know, when you hit an oil well, what comes out of this oil, the last thing that comes to the wellhead is natural gas, right? So watch for people in places they're doing natural gas, like Qatar, places like that, or Alaska. So last year, was it December of 2021, the Army Corps of Engineers approved a giant natural gas pipeline from the North Ridge going all the way down to Anchorage across Alaska. So what does that mean? Oh, that tells me that Purdue Bay is going dry because of this. When they find an oil deposit, how that works is, first of all, they have this cap rock that's impenetrable. The one thing about these deposits, you got to understand, the pressures are incredible. They're usually greater than 20,000 psi. So on the top of this oil deposit is gas, and the pressures are so high, it's actually not like natural gas, but like butane or methane or whatever. The pressures are so high, it's compressed into a liquid and under this cap. And then below that's the oil, and then as you get deeper down into the oil deposit, it turns into this heavy sour stuff. It's got a lot of sulfur in it, and the very bottom of it's asphalt, and the bottom of this oil deposit, right? So when they find a deposit, the first thing they do is they figure out where's the exact center, right? That's where the gas is. They cap that well, they don't touch it. They drill around the edge of the oil deposit, and the reason why they do it that way, they use the pressure of the gas to push the oil to the surface. Once the pressures drop to the point to where they've got a pumper jack out there, they'll put pumper jacks out there pumping the oil out. The other thing they do is they start pumping water down in there to push that oil. That way, you got water, oil up against that gas gap. The last thing that they pull out of that deposit is the gas. So the sheer fact that they're pulling gas out of Alaska tells me she's on the downward slope and she's going right.
Hey, Dan.
And the Gulf of Mexico, Persian Gulf's the same way. Go ahead, Stan. Sorry.
No, Peter had his hand up for a while, and I wanted to make sure he could wrap it. Plus,
No
we're
worries.
at the
Go ahead, Peter. I'm
5:30
sorry.
point.
Oh, no worries.
You asked me that question. I just gave you the answer, and the answer is
yeah.
there's a catastrophe coming. Yeah.
Dan, one thing for sure is I am going to go back and I'm going to listen to what you just said at least 2 or 3 more times, because there's a wealth of knowledge. I just, one of the things I wanted to mention was, was that, certainly, Matthew Simmons had written Twilight in the Desert, what,
Yes.
16, 17 years ago.
Yep.
I had a chance to sit with him and, I think in 2007 and doing an interview for a documentary. And many of the things that you're mentioning, he was talking about back then. But with relative to Rystad Energy, which you mentioned a little bit earlier, they just, I think on the 30th, they published a press release where they're at the last 2 years in a row, they published, their post BP statistical review and IEA and EIA, all that stuff. They've published their analysis of those other things. Last year, they said recoverable reserves were down 9% year over year. This year, they said year over year, it's down another 9%. What they also said was that they define what technically recoverable reserves are, and then they start talking about proven reserves. They pointedly said that proven reserves will be exhausted at the rate we're consuming them today. They will be exhausted between 10 and 14 years from now.
Yeah.
That is, I think that's the global economy.
Yeah. And you're saying 10 to 14 years, and I'm going to tell you something that'll disturb you. That 10 to 14 years, but that 10 to 40 years is well, let me put it this way. 10 to 14, but I'm going to say that part of that's probably a dream. Let me give you an example. Here, let me give you an example why.
Sure.
It might be sooner than because understand, I'm one of the guys, I've got computer systems because we have equipment on wellheads. Okay. So I've got like the Evansville oil and gas field, the Shelbyville gas field. You watch the videos that Stan and I did. I show you maps of those fields. Here are the producing wells. Here are the dead wells. Right? It's in the video. You can see it for yourself. I actually show people that stuff. But so we have equipment that measures the oil and the gas coming out of the wells. And the reason why is because there's tax money being paid on those and royalties. So I track these things, the production coming out of these things all the time. And one of the things I pay attention to is what's going on down in the Gulf, because we ship gas from the Gulf all the way up here, and we store that gas down in Evansville. We use a lot of those depleted gas wells to store natural gas from the Gulf. So in the springtime, we pump gas up from the Gulf of Mexico and store it up here, up there in Evansville, for for storage up here, underground storage, which store the gas. Well, one of the problems out in the Gulf is simply this: because they're going 300 miles out or farther from the coast, and the water's 3,000 feet or deeper. Okay, the insurance companies don't want to insure the risk. Yeah, you chew on that. There's one of the big things that Biden gets beat up, says, oh, well, he put up all these leases and he took them for out in the Gulf of Mexico and he's a bad guy. I'm like, no, he took them off because nobody wanted to take the leases because the insurance companies don't want to insure the risks. And the reason why is because when you're 300 miles or farther out and the water gets deeper and deeper and deeper, the risks go up and up and up. There's another piece of this too. And this goes back to those recoverable reserves. Unless the oil deposit is 100 million barrels or larger, it is not economically viable to go after it. Right. So there are a lot of deposits out there, but they're too small to make it economically feasible. And the other thing is with our drilling with our sounding technology and the computers and the geology, a 100 million barrel oil deposit is easy to see, guys. There's just not much out there. I mean, there's a lot of small stuff.
Yeah, 100 million barrels is, if you could extract it immediately, that's a one-day supply. We're using we're using now at 100, 100, 101,
100 million barrels a day.
a day, right?
Yeah,
I mean,
The,
is
the
the flow
planet
rate,
Earth
but
burns 100 million barrels of oil a day.
but that is also something that flow rate is on demand. So as you were mentioning earlier, the headroom, the excess capacity is virtually zero. And so, basically global GDP tracks energy consumption with a variance of about 1%.
Yeah.
The global economy, 100% of the heavy industrial transportation requires liquid fuels. So, I mean, what you're talking about is that we've got this economy that is going to start contracting irreversibly, and it's virtually immediately.
It's actually worse than that. Stan has a paper. A friend of mine, Jerry McFarland, and Jerry passed last year from COVID, but Stan there's a paper that Jerry and I wrote about 3 years ago. And basically, the idea of the paperwork has to do with all the projects that the Chinese and the Russians and Iranians have been building, all these refineries and pipelines and so forth. And Jerry and I came to the conclusion by 2025 we were going to be buying fuel from our enemies. Okay. And that was the first story. That was the first show that Stan and I did. We talked about that paper. So if you want that paper, ask Stan. He's got it. Right. And that was a paper we submitted to the Department of Defense and the Department of Energy and Homeland Security. So all those directors know about that because we talked about it. Now,
I think Richard had a question too, Dan. So
go ahead.
Yeah, in Hawaii, we're going to be over the hotspot for 1 to 2 million years, and we don't have any fossil fuel on the ground. So, when the steam comes out of the ground, there's no carbon associated with it.
Right.
So we are incredibly lucky because it's under pressure. We have water underneath there. It spins a turbine, and it doesn't have any of that stuff.
Well, all this type of geothermal energy, geothermal power is available anywhere on the planet. But give me a second here. Go back and talk about that oil thing you just talked about. We're actually in a very perilous position right now. Let me tell you why. One of the things that happened in April 21st of 2020, the oil markets crashed, and that was minus $37 a barrel. Okay. Russia pulled 4 million barrels of oil production offline to get the prices up to $55 a barrel. And they did that for 10 months, right? And then to the end of 10 months, in the year 2020, they brought that 4 million barrels back online. And so I did a bunch of calculations, and I basically postulated, I think the Russians have the ability to pull 5 million barrels of oil production per day offline, and it didn't affect them. They didn't have to shut in wells. It didn't seem to affect their economy. And that's when oil was like $55.
Yeah.
Last week, last week, JP Morgan Chase came up with a paper, and that's exactly what they said. They said Russia can remove 5 million barrels of oil production per day offline, and it will have no material effect on their economy.
I just have a question because in many cases there's a situation when you pull oil production off, you have shut in wells. You have wells that will never come back to life again. Are you suggesting that they're able to do that without affecting the productivity of their fields?
Well, first of all, they kind of mischaracterize it. They say it won't produce again unless they go back and drill it. In the case of the Saudis, in the case of Russia, because these, especially the wells up there by the Urals, that's up by the Arctic Circle, these things will freeze solid. So that oil in that pipe, from the wellhead down about 100 yards, will be frozen solid. So that means you got to send a crew out there and re-drill the well. It's not that it won't produce again. It's just got to go re-drill it. Okay.
Okay.
The other thing you got to remember is you're not dealing with a company. You're talking about a sovereign nation.
Right.
Vladimir Putin sitting on a central bank, and everybody has this misconception about money. And I have to point out, if you pull out a $20 bill, that is a Federal Reserve note. It's a bank. I had this strange concept about money because I deal with the computers. Everybody says, well, I have so-and-so money. I said, no, you just have numbers in a computer someplace. And I said, that stuff you think that's money, that's just a bank note, right? Well, Vladimir Putin is sitting in a central bank, and he can loan as much money into existence as he wants and tell a bunch of his Russian guys to go out and drill wells and pay him in rubles, right? And he can make debt disappear because he owns the central bank of Russia, and Russia has oil and gas and gold and all these other assets. I said, so
He's following this. He's following the same model that the United States did with the Fed, and yes, I mean we taught the world how to do that.
yeah,
And
yeah, we're behind the eight ball,
Hang on,
guys.
Richard's trying to get in.
Dan, I'm just now talking about Hawaii, yeah, because we're sitting out here at the end of the supply chain in the middle of the largest ocean in the world. We're vulnerable, yeah, and we rely, we import 85% of our food. But one thing we do have, and this is, you know, there's going to be a letter to the editor, op-ed piece for a civil beat, and I wrote it, yeah, and addressing this exact problem. And I'm asking them why, when we have oil for 1 million to 2 million years, and it's got water underneath there, it's got heat, it doesn't have fossil fuel, it doesn't have any carbon. Why aren't anybody doing anything about it? We've known that for 10 years. But everybody talks about everything else, but we're not everything else. We're Hawaii in the middle of the Pacific. And on the mainland is different, yeah, of course. All kinds of different things going on. But us guys, we have that.
Well, Rich,
what my question is,
go ahead.
Isn't that a big advantage? Isn't that a big advantage?
Yeah, well, the other thing, Richard, and is I talked with Stan, what we're talking about, especially the geothermal stuff, is it doesn't matter if you're sitting on top of the hotspot. All you need to do is just, we could do this on an atoll down in the French Polynesia, right? All we need to do is just drill down to those depths, and you'll be able to realize, because that's just the heat of the crust. I mean, the center of our planet is molten, right? So there's this power source you're sitting on, and really you just need to get a drill crew to go out there and drill you some wells down to 30,000 feet. So you don't have to be on the top of a hotspot. But yeah, everybody is sitting on this huge energy source, and you should be taking advantage of it. And if you couple and I've been doing calculations, you could do a geothermal power plant and probably produce electricity for about $5 a megawatt hour. And you say, well, how is that possible? Simple. You're not paying for fuel.
Marketing,
All you're paying for is
advertising,
parts.
advertising.
So that's still my same question, yeah? That is, and I hear exactly what you're saying, because you got different levels that you got to drill, yeah? Ours is only less than 10,000 feet.
Yeah.
Well, the thing is, you got to remember is, well, and, you know, like I said, you've got some of the islands that are not over the hotspot, okay?
No, wait a minute. You know, when we went to the Philippines, I was on the trip with the former mayor, Billy Canoy, and we were on top of this volcano that last erupted 100,000 years ago, and they had the geothermal plant on top of that. Mauna Kea erupted, Mauna Kea last erupted 4,000 years ago. So there's a lot of heat, you know, and we got 5 volcanoes on this side.
Yeah, the difference there is the Philippines sitting on top. There's a subduction zone right off the coast there, and there's a huge trench out there. So there's always volcanic activity because that's subduction. But you're right in the middle of a plate, right? So you only have to worry about the big island, which is sitting directly on that hotspot. All the other Hawaii islands, you know, from Maui to, you know, etc., they're not sitting directly on the hotspot. All you have to do is anywhere on the planet, if you go down about 5,000 feet, everything from the top down to 5,000 feet, most of the planet is what we call sedimentary rock. Below that is basalt. That's that thick black volcanic rock that doesn't have any little bubbles in it, right? If you drill down into that, down to those 20 and 30,000 feet, just the heat of the rock itself is that hot. Because the deeper you drill down, the higher the temperatures. So you don't even have to even be near a hotspot to even make any of this work.
Yeah.
So
let me kind of tie this together, Richard. You know, you're thinking of Nicole, Lautzi, and those guys drilling test wells to find the right spot, but the reality is, in a lot of the places on Oahu and Kauai and maybe even Maui, you don't have to drill a test well except right next to where your power plant is to make sure you're not getting into the wrong geology and messing things up. So your point, enough. Richard, is we have plenty of heat, and we will for 5 million years. We got plenty of heat. The question is, are we going to spend all our energy trying to kill oil and natural gas? Or are we going to spend all our energy trying to go forward and build the power generation that's going to replace natural gas and oil? And
Yeah,
that's
exactly.
the problem.
Richard,
here's another thing. Here's another thing. All the islands have heat. It's relative, yeah. So it's a young. Big Island is younger, so it's the hottest. But let's assume, we do some exploration. They do surface exploration to just get an idea what's underneath there. Wouldn't it be good to have every island independent? Have so much of base power. Yeah.
Yeah.
We don't have to worry about.
Yeah. In fact, that's one of the things Stan and I talked about, is that every little town probably needs to have between a 50 megawatt to one of these, 300 megawatt little steam power plant, a geothermal power plant. Yeah. Richard, let me give an example. I live here in Indiana. I go over to Ohio where they're drilling those shell wells down to 20,000 feet. We have water coming out of the ground at 300 degrees Fahrenheit, and we're nowhere near a fault or a hot spot. And water's coming out of the ground that hot. We're injecting into one well, and the water comes up in another well, right? And it's coming out of the ground at 300 degrees Fahrenheit because those wells are drilled down at 20,000 feet. And some of the wells, for example, down in Oklahoma are drilled down to 35,000 feet. And I've got data on wells down in Oklahoma drilled down to 35,000 feet, nowhere near a subduction zone or a fault or anything like that. And the water is coming out of the ground at 500 degrees Fahrenheit.
Hey, Ron Riley has a question.
Ron's got a question.
Thanks,
go ahead.
Peter.
Hi, Ron.
Yeah, I hate to break in because this is so darn good. We should go for another hour or two here. I guess, Dan, I just finished reading a book that I think is relevant. It's called Blowout by Rachel Maddow. And she talks about Putin and Russia and the Arctic Circle and what he's able to do up there with or without Rex Tillerson and ExxonMobil. And so I don't know how those reserves figure into your calculations here of 10 to 14 years. That's one point of the book. And the other point is the fracking. And she goes into several chapters about Oklahoma City and the earthquakes and all that. And the top oil guy down there, I can't remember his name, drove his SUV into the abutment of an overpass and died in a fiery wreck.
Yep. I know what you're talking about, yeah.
No reason at all. And basically here in Hawaii, the huge scale of the 2-foot diameter pipes and the Gulf of Mexico oil rigs coming up somewhere near Waikiki or wherever, it just boggles the mind. And we already have maybe an uninformed opinion of the dangers of fracking. I mean, PGV, our local geothermal, is facing fracking criticism, and they don't frack, and they're facing fracking criticism. So I guess what I'd like to know is, have you read Rachel Maddow's book? Is it kind of on track or is it not? I don't know.
I've read, I know what you're talking about. I've
read it. So
yeah, I disagree with it. Understand the stuff I'm talking about. I use hard data besides the stuff that comes out of my computer systems, and also the stuff that Peter and I are talking about, and Peter Simmons and Art Berman, and these are people that are in the business, and the International Energy Agency. Yeah. These are agencies that are saying this. The Department of Energy saying it. So it's not this woman's opinion. As far as horizontal drilling and fracking, ladies and gentlemen, I hate to tell you this, but that technology has been around since the 50s. Go out onto YouTube, look up T. Boone Pickens. He did a TED Speak. And T. Boone Pickens, I think he tells you he graduated from the Oklahoma State in like 1955, and he'll tell you he fracked his first well in 1957. So the horizontal drilling and fracking has been around for a very long time, and it doesn't seem like anybody had any problem with it until probably the last 10 or 15 years. And a lot of it just has to do with somebody decided to crank up a lawsuit. That's what I say.
Well,
And
that's why I say,
the oil and gas companies are willing to pay these people off.
if we didn't spend so much energy trying to kill oil, because bottom line is we're burning it, we're going to run out at some point, and no matter whether there's oil under the Arctic or Antarctic or wherever, you're still going to run out at a certain point. So why are we're going to suck it all dry before we finally figure it out?
Stan, here's another thing though. I mean, the entire planet, except for, well, the entire planet is trying to kill oil. Okay. The problem is that the systems necessary, or the systems that are being utilized, cannot be produced without oil.
Right.
So if you kill oil, you kill those systems. When you talk about renewable energy, you're talking about the feedstock. You're not talking about the sustainability of the system that transforms that renewable energy into work. The work we have to get done.
Right. One of the reasons why we had this huge debt bubble in our banking system is because the oil and gas we have out there, because of the expense of bringing the surface, it's not as profitable as it used to be. And what's happened is the bankers have been trying to paper over this problem with cheap financing. Give you an example. I mean, 30, 40 years ago, we'd go out there and drill a conventional oil well. It might cost $700,000 to drill a well that'll produce oil for 20 or 30 years. When these guys go out there and do the horizontal drilling and fracking of shale, okay, those old oil wells, 5,000 to 7,000 feet deep. Shale, it's 20,000. There's one. The second one, to drill a well, it's between $7 and $10 million per well. That's whether you find shale or not. They cost you $7 to $10 million to drill that well, just to drill it and frack it. It's about $4 million to drill it, $6 million to hydraulically fracture the rock. Okay, the second part of it is that, well, the first 12 months, 60% of your production is in the first 12 months. And the remaining 40% of the production of that well occurs over the remaining 60 months. So by the time that well is 72 months old, it's dry. So you spent $10 million on a well that's only going to produce for 72 months. And the oil that might come out of that well came out in the first 12 months. That remaining 4% is just gas. Well, ladies and gentlemen, that's real expensive gas. And so the guys are talking about, they want to go, we want to go over here in Ohio and drill for more gas. Nobody wants to drill gas. Why? Because to take advantage of gas, you spend all your money putting infrastructure on a well that's only going to produce gas for 72 months, and then she's dry. The reason why nobody wants to do gas is because you can't make any money doing gas because of all the infrastructure you have to put in just to get the gas out of the ground. And for a well, it's only going to be around for 7 years. So the biggest problem they have in the shale gas thing, it's like I had a big blowout probably about a month ago with the governor of the state of Ohio. And he was basically talking about, we need to get guys in here and drill some more shale, right? Well, the guys took me up there. They gave me a box, got me up there so I can participate. And the first thing I do is I pull up the Ohio Department of Natural Resources website, pull up the well tracker, and it's got a nice little graphic, shows you where all the wells are in the state of Ohio. It's got Google Maps on the back end. And my question to him was, where have you not drilled? I hear crickets. Yeah. Where have you not drilled? Oh, you didn't drill in the strip mall down here? You didn't drill in somebody's subdivision? You didn't drill out in the middle of the freeway? You get the problem here? They're renting in real estate.
I used to go out and I used to shoot video of stuff, and I have a beautiful shot right into the sun of an oil jack going up and down, and it's like I pan over about 50 feet and I'm looking at a McDonald's. It's in a parking lot. Huntington Beach, the city hall in Huntington Beach has oil wells pumping oil in their parking lot.
Drive through Long Beach sometime.
Trust me, I have. As a matter of fact, the McDonald's
Los Obispo up in California. My uncle used to live up there. There, the Safeway, right next to the Safeway, there used to be a pumper jack. They used to pump oil for like 20 years. The last time I was there about 3 years ago, they took the pumper jack out and sealed the well. But they don't last forever. But yeah, I remember a pumper jack right next to a Safeway shopping, places
So
where you're going to buy food and stuff. But
yeah, the thing that the thing we're doing is we're not distinguishing between, I mean, we're talking about energy, and we're talking about renewable energy. We're talking about primarily electricity. We're not talking about transportation fuel. And for me, for a long time, I've been, my thing is like, that we're railing about carbon, and I understand carbon is a problem. But the thing is that without transportation fuel, or without something to replace that transportation fuel, we can't mitigate carbon by any other way. Rystad itself is saying the decline in available oil is going to mitigate the carbon problem just by attrition.
Yep.
Well, here's some numbers. So those traditional oil fields, like the United States, we produce 4 million barrels of oil a day by traditional oil wells. Those declined by 6.7%. Yeah, 6.7% per year.
Per year, yeah.
The shale wells, they declined by 6.3% per month.
No, they're very short term. I mean, you've got Gowin has been pumping for 80 years and it's still active. I mean, when you the Permian is the only area that is prolific in the United States. Shale oil has been responsible. Shale oil has been in the United States has been the single most productive ability to increase the global volume over the last few years.
What everybody misses about it, the source rock for that oil was the shale, and above that were those oil deposits. Well, like West Texas, we depleted out the oil deposits. So when they're out there drilling shale, they're drilling under those oil deposits to get at the shale. And that shale's at 20,000 feet. The only place that's left is around Midland, Texas. That's it.
So to hit Peter's point, we're moving towards electric power, whether it's transportation or whether it's, the grid. And if you... And that doesn't matter whether it's plug-in electric cars or hydrogen fuel cell cars. The bottom line is we need to get into producing electricity, twice as much, at least, electricity as we do now, to make all of our electric grid requirements and to start converting our vehicles to hydrogen fuel cell or electric.
However, mining vehicles, large transoceanic vehicles, these are not going to run off the grid. But we need liquid fuels to do that.
But I spent the last 10 years actually solving the problem you're talking about. The reason why I invented the Electrum hydrodynamic compressor was actually to solve this. Originally, I'd started out with solving a problem with the power grid, and it had to do with when I worked at General Electric and I was working for alternative fuels program that was burning hydrogen in gas turbines. Okay. So in the state of Indiana, I'll give you an example. We curtail 7 terawatts of wind every year. Wind's blowing, we're not using the power. Well, if I can use, for example, Chris McWinney, Millennium Rain Energy, if I use his megawatt grid scale electrolysers, this is an electrolyzer that fits in a 40-foot cargo container, right? And that's 1 megawatt is 22 kilograms of hydrogen per hour. Well, I can turn 7 terawatts of electric power into 152,000 metric tons of hydrogen. And I got plenty of depleted gas wells to store that gas. And if I could just store that gas, I can burn that gas in an LM6000 gas turbine, put those all over my power grid, and solve my peaker problem. Okay? With like in August, when everybody's using their air conditioner, I can fire up a gas turbine, burn some hydrogen, generate electricity, and solve that issue. What I didn't realize by coming up with that graphic, my PowerPoint presentation, that's what that graphic is. That's a hydrogen park. Okay, that's what it solves. I actually end up solving a bunch of other problems on top of that.
Yeah, that's where I was going with it. Was that the transportation fuel problem is solved by hydrogen?
Right.
One of the had to do with the compression. I had to invent the compressor. The Electrum hydrodynamic compressor is designed per compression cycle, moves 15,000 liters of volume, and is actually engineered to pressurize the gas to 60,000 psi, right? The wells, if I pump the hydrogen into the wells, I can pressurize the wells to 1,000 bar. That's 15,000 psi. The Toyota truck or the Kenworth hydrogen fuel cell truck, they only require 700 bar. I'm already pressurizing the gas at 1,000 bar. because that's what I'm using for the power grid. And I'm already generating gas in industrial quantities because I want it for my gas turbine. Okay, so that solves transportation fuel. And if I locate these parks right next to like freeways and stuff, you know, I can put in pipelines and stuff like that. I can solve the transportation fuel.
And actually, there's mining trucks and such now that are actually being built to run on fuel cells. So not only that, but you can make liquid fuels out of hydrogen.
Mitch's hydrogen airships is going to solve the
That's true.
transoceanic freighter problem.
That's why hydrogen is key to all this.
Yes.
But the big thing you always hear, like from Mitch's boss, Rick Rochelo, is it doesn't pencil out. Because if you don't have electricity that's cheap, you're not making the volume of hydrogen you need at a reasonable price. Right. But that's where the geothermal piece comes in. Because when you start thinking, I'm not paying for fuel for the next 100 years, and I make an upfront, expense of capitalizing the holes I drill, and everything else, it doesn't really cost you a lot of money. You have stable.
It's no different than the oil business.
Exactly, except that we don't have to burn fossil fuels and waste fossil fuels because we're just recycling heat out of the core of the earth.
I was talking about just the economics. The economics for geothermal are so much better than the oil and gas.
That's the reason why. So, I mean, even when I did, Stan's got my spreadsheets and calculations, because I'm the guy that designs those energy markets and the power grid and those type of things. And that was just buying wind power and I can buy wind power contracts here for $15 per megawatt hour. And when you're producing hydrogen using that, I can drive the prices down to like 80 cents per kilogram.
Yeah, well.
I haven't even started in on converting the existing power plants over to geothermal, and then I can drive it even lower.
Yeah, I mean, what you're talking about is a business model. Like I sat and I had a conversation with a number of people at Hawaiian Electric on Tuesday, and it had to do with about how to get to hydrogen, and the question came up was like, what do you want from us? And essentially, it was virtually nothing, at least at this point, because in order to produce that, you need to make your own power. You need to circumvent what we have here in Hawaii, which is the monopoly that the utility has over selling electricity.
Bingo.
But Peter, one of the things I'm going to do, and I'm going to talk with Stan about this, I have this tool, and the back end of the tool that I have is tied into the Department of Energy. And what I'm going to do is Stan on a live show is I'm going to pull up the tool and I'm going to do a live analysis of your power grid. Live.
Love it.
All your high tension power lines, your generators. I'm going to click on it and know exactly this generator is producing this much power right now. Here's how much power you're running over that high voltage line. And I'm going to go through and nitpick through your power grid. That's what I'm getting at. Right?
Hey, Stan, be sure that I have a link to this one.
What we're going to do is we're gonna. I only did that one show on Rumble, and we posted it. And I think I gave it to a couple people, but
I got it.
Yeah. So that was our first takeoff, and we're gonna do. Maybe once every 2 weeks we'll do another show. We'll do that one, and I'll put the link out there for everybody. I mean, for me, I'm getting old, and I don't feel like doing shows all the time, but these are so important. I figure we got to do some and put them out there, so we will.
Well, I understand whenever we do this, it'll be recorded and we'll put it up on Rumbles for everybody to see. But I already know right now doing that, my critique is A, you need an ISO, B, you need a power grid. You need to pull Siemens in there. You need to put in undersea power cables, and you need to link all your island and grids together into the big power grid across all those islands, okay? You put in an ISO, an independent systems operator, non-for-profit. You put in an energy market in there, and you open it up and let everybody compete.
I hate to do this. Ron has a question, and then we were supposed to end at 5, and it's now after 6. So, and I could easily go at least another hour.
Well, it's a Friday night, guys. So
Dan's kind of addicting.
Absolutely.
Let me just throw out a couple of data points here. We know from 11,000 feet on our big mountain here, Mauna Loa, the home of the Keeling curve. We know we're at 420 parts per million. In 1958, when they started measuring, it was 315 parts per million. We've had a 30-something% increase in my and your lifetime. That's a worry to me. Now, that's one data point. Now, the other thing, Richard has been telling me for a long time that we're going to run out of oil, that peak oil, and your data seems to confirm in my mind.
I have my own calculations and charts. I zip those up. I send them to Stan. Stan, you're free to give them to those guys and see the numbers.
Okay.
You can shoot on it.
So
the reason why Russia did what they did is because they're close to peaking. That's why Vladimir Putin pulled some of the crap he did.
Yeah. So here's my third data point. You've got the CO2 in the air. It's rising faster now than it's ever risen. And you've got the peak oil, and there's, your graphs are going to show that. On the other hand, we've got a state law that says now, in conjunction with President Biden's goal, we want to reduce our carbon emissions by 50% over 2005 by 2030. Is peak oil going to mean that we can achieve that goal of CO2 carbon emissions without doing anything? Or do we have to put in a carbon price like Citizens Climate Lobby and I would recommend?
So let me answer your question. In short, and here's what I tell everybody. There's plenty of oil out there. The question is, what do you want to pay for?
Yeah.
$20 gasoline, you're not driving.
Yeah. I think that's going to actually drive it more than anything else is, we're hovering around $5 to $5.50.
I'll make a prediction. Right. By January of 2023, it'll probably be very close to $10 here in the States. And Hawaii is going to be higher than that.
Yeah.
Yeah. So
that's right now.
What the point that you're making, Dan, is really what it is. It is driven by the economics. And when you hit $100 oil, it becomes recessionary on a global basis because it's a global commodity. There is a player out there in Europe. His name is Vladimir Putin. And if the Europeans and us, we don't play ball, he has the ability to remove 5 million barrels of oil production per day offline. And that'll, according to JP Morgan Chase, that'll drive oil to $380 a barrel. Right.
That will crash our economy.
Right. Yeah, because it's not a linear. The relationship between availability and price is not linear.
Because nobody has 5 million. There's no way to make it up. Not only that, but the oil that's out there, the fields are declining, and they're declining quickly. So it's only going to get worse. Yeah.
And with interest rates, you can't afford to finance the drilling of test wells in weird places to go find more oil. So it's a perfect storm.
So the bottom line is whatever we're going to do needs to be local. It needs to be regional. We need to focus on where we live, and we have to do it really quickly because business as usual is how we got here, and it isn't going to solve the problem.
Right.
Yeah, down south, down in the Dutch East Indies, Indonesia, there's the oil fields are down there. Last year they were talking, generally they produce about 4.5 million barrels of oil a day. This year they're only going to produce 3.8, and they have been out there drilling, trying to find new stuff. The only thing they're finding is gas. They're not finding oil. Yeah. So those oil fields down there in Indonesia, North Australia, Malaysia, Indonesia are going dry. The point is you're going to have some hungry drillers here for the next 2 or 3 years. So if you're going to strike, this would be a good time to strike. 3 years from now,
Baker Hughes.
They'll be out. They'll be gone. Yeah.
Baker Hughes. So the same thing's happening with the North Sea, and they're in the middle of decommissioning.
Oh, the North Sea's in decline. That's why Europe's in trouble.
Yeah.
The Cantrell down in Mexico is in terminal decline. The North Sea's been in terminal decline for 20 years, guys.
And I think solar panels will be great, and we should probably have some. Wind, I don't think is ever going to really take off in Hawaii. I speak to Senator Riviere from the North Shore, and I can tell you the people that have to put up with those turbines on Oahu are fed up, and they don't want to do it. But even those turbines, they don't last that long, and they're expensive to build, and they last 15, 20 years. They're really maintenance intensive, and in this salt environment, they're going to wear out even faster. So we need something like geothermal, which is a long-term investment that we know we can get the funding for when you have 100 years, you can amortize this stuff out for and start going that direction. And we're not doing it right now.
Geothermal is also something that can operate low tech. It's not something that requires,
Chips and
it can be done low tech. Richard has something that he wants to say.
Yeah.
Dan, just recently, a group of 6 companies, world-class companies are talking about ammonia for maritime fuel. And it looks to me like if we did geothermal, and it's green geothermal, we can get to green hydrogen. We get to green hydrogen, we get the heat, we can get to ammonia, because all of that is dependent on geothermal, right? What do you think?
Okay, let me answer your question for you. This goes back to one of my happy accidents, something I did. Okay, and actually Stan and I did a whole entire show on ammonia. Okay, so and I go into the history of the hopper process and how they make ammonia and so forth. So let me describe to you the optimal condition for making ammonia, anhydrous ammonia. The optimal conditions are 1 part nitrogen, 3 parts hydrogen, okay, a reactor using an iron catalyst, and you need to have like aluminum oxide and copper oxide as impurities in your little iron pellets in your reactor, and 1,000 bar pressure. Okay. Well, one of the problems they've had since the hopper process was built, they were never able to build a compressor to compress hydrogen to 1,000 bar, which is 15,000 psi. They were limited by because the compressors that they have, the reciprocating compressors, only go to what, like 3,000 psi. Well, because those compressors only go up to 3,000 psi, they have to heat the reactor up to 900 degrees Fahrenheit. So the reason why the process that produces anhydrous ammonia consumes so much natural gas is because they have to heat the reactor up to 900 degrees Fahrenheit to make the catalyst reactive enough to react with the nitrogen and the hydrogen to produce ammonia. Now, the Electrum hydrodynamic compressor, when I store hydrogen in those gas wells, is stored at 1,000 bar, 15,000 psi. So if you build my hydrogen park and we grab a hopper ammonia reactor, we could producing anhydrous ammonia cheaper than you could ever produce it using natural gas. The other thing too, I didn't tell you. So it's 1 part nitrogen, 3 parts hydrogen, right? That iron-based reactor I told you about, 1,000 bar, 15,000 psi. The reaction in the reactor occurs at 70 degrees Fahrenheit. That's room temperature. So you'll have a reactor producing anhydrous liquid ammonia at room temperature, and you just drain the liquid ammonia right out of the reactor because the ammonia turns into a liquid at about 125 psi. Right? It actually requires less energy, and it's just plain safer to do it that.
And there's
so
a couple
believe it or
reasons.
not, that was a happy accident on my part when I built the compressor.
And there's a couple of reasons that ammonia is so important in this equation, and why Richard keeps bringing it up. And that is, number one, if you're going to have cargo ships running on hydrogen, they're probably going to be using ammonia as their fuel.
Yeah.
Because it's easy for them to meter out and carry in their cargo holds without changing all the plumbing in their ships. Number two, we're agricultural here. We want to stop importing a bunch of food. We want to start growing more of it, but we need fertilizer, and hydrous ammonia is a key component in fertilizer. So the hydrogen piece stores your grid power at the scale you want at a cheaper price than batteries and safer. We can make ammonia for agriculture and just put in ships, and maybe even some of the aircraft drop-in fuels will be ammonia too in the future. And right now, aviation that comes in from outside the state, they have to refuel here. The Kahi Power, the Campbell Industrial Park power plant or refineries, half of the fuel they make is for aviation, because all of the jets that come in from Japan and Asia and Europe and the mainland have to refuel here. So ammonia will be a key component as a liquid drop-in fuel for airplanes. All these things add up to why hydrogen and geothermal make sense.
One of the things that kind of those other happy accidents, when I was working at General Electric on the gas turbines burning hydrogen, we tested all these different fuels. I mean, we went down to a Wendy's and pulled like chicken grease out of the big trap in the back. We were burning vegetable oil in gas turbines, you know. God, smells like a Kentucky Fried Chicken. And like, well, yeah, because we got the grease from a Wendy's that we're running through that gas turbine, right? One of the fuels we ran through the gas turbine was we burn ammonia. And one of the things we found out, if you put ammonia in the tanks and you pressurize it to 300 psi, ammonia turns into a liquid at about 125 psi, okay, right? But when you compress it to 300 psi, it is a liter for liter, gallon for gallon equivalent to jet fuel.
Yeah.
Actually, it's a better fuel than jet fuel. And the reason why I tell you it's a better fuel than jet fuel is that jet fuel, there's this what they call stochastic fuel-to-air mixture, right around 33%. And if you're very out of it, the engine will flame out on you, right? But ammonia is like hydrogen has a stochastic fuel-to-air mixture between 4% and 75%. Ammonia is a little tighter. It's between like 20, it's like 20 and 70. But the point is, it's hard to get a flame out on an engine burning hydrogen or burning ammonia. And so one of the things we're probably going to, and I've already gone back and forth with the guys at the Department of Energy about this, what we're thinking about, taking our existing aircrafts, redesigning the fuel tanks so we can pressurize them to say 350 or 400 PSI, and we start using ammonia in jet aircraft.
Yeah.
Right? And as far as the ships, we can put a gas turbine on a ship, right? Use that as to generate a power. Most ships these days are hybrid electrics. Below the ship, they take a big induction motor and it dangles below the ship, and it's got a propeller on it. They use it to directionally propel the ship, most of the ships these days. So what you've got inside the ship is really just a big generator. So if you use a gas turbine tied to a generator and you're burning anhydrous ammonia, that'll power your ships.
Yeah.
So this is solving a lot of things. A lot of things.
Perfect. Okay, Peter, over to you. You're in charge and we're running late.
Hey, we're done. I'm hungry. So, Dan, this was beyond. And I want to thank you very much. And I'm dead serious about watching this more than one more time. Lots of information and yeah, a lot to think about, and we will be talking again soon.
I had fun.
Anybody else have anything to dive into before we go?
Just thank you so much. That was great.
Excellent.
Yes, thanks, Dan.
We have a future.
Yes.
We do have a
If
future.
we act quickly, right?
We have to act quickly.
One of the reasons why I had a couple of directors at Jet Propulsion Laboratory and Redstone. I'm not dropping names and stuff and saying who they are. The reason why they dragged me into this thing because these guys knew that I am into building really big stuff. You know, that system there at MISO. When I worked for the Department of Navy, I built the Aegis battle management system, right? And of course, working the ArcNet project, GPS, all those things. So this is the kind of stuff I've been doing for a long time. And somebody asked me one time, it's like, Dan, how'd you walk down this path? I said, sometimes God comes along and fates people and curses them to do these kind of things. So
it was one step at a time.
It was one step at a time. Like, how'd you fall into this? I fell into it. Literally, I never thought it would happen that way. But
yeah. Well, thank you very much. We will be talking again. Anybody else have anything? We're good. Thank you.
Okay, Dan, thanks a lot. Hello, everybody.
Don't worry, guys. There's solutions. We can fix it. Trust me. Build.
Save the